In this video we're going to look at the Opamp. So what we have here is a typical integrated circuit Opamp. So this is a 741, and you can see here it's got 8 pins, and I've got the pin out over on the right hand side. So as this is an introductory video, don't worry too much if there's terms in it that you're unsure of, as we're going to be going over them over the rest of the videos. Okay, so in this pin out here, pin 8 is not used, pin 5 and pin 1 are null offsets. I'll go over that in a different video, we don't need to worry about them for the moment. And there's 2 inputs here, so there's an inverting input pin 2, and there's a non-inverting input which is pin 3, and there's an output which is pin 4, and there's another 2 pins here which are the power supply rail. So there's a positive power supply pin 7 and a negative power supply pin 4. Okay, so that's the basic little IC for a typical Opamp. Now, what does this Opamp do? Well, quite simply, it takes the difference between the 2 input voltages here, it multiplies it by a huge gain, typically of around 100,000, and it puts that out as an output voltage here on pin 6. So that's the basic of an Opamp. So that's why it's called a differential amplifier, because it amplifies the difference between the 2 inputs. So mathematically we could look at it and we could say that the output voltage there is going to equal the difference between the 2 input voltages times a huge gain, where that gain is of the order of 10 to the 5. So let's go ahead and we'll stick some values into that and we'll see how that works. So if we were to hook up the power and supplies to a plus 12 volts, minus 12 volts, and we were to make the V plus side equal 1.001 and the V minus side equal 1 volt, then from the equation above, quite simply, the Opamp takes the difference between these 2 voltages, which is going to be a small positive number, multiplies it by a huge gain, which is going to give us a value of 1000 volts. So obviously we're not going to get 1000 volts at the output, because the output only goes up to 12 volts. So it's going to tend to push the output towards 12 volts. Okay, so we'll get 12 volts there on that output. Now, if we were to do it round the other way, if we were to put the 1.001 volts on this pin here, the negative pin, and the 1 volt on the positive pin, then we're going to get a number, but it's going to be a very small negative number, and if we multiply that by 10 to the 5, we're going to get minus 1000, but obviously we're not going to get minus 1000 volts in output, we're going to get just the power supply, so we'll get our minus 12 volts in output. So you can see here why they get the names inverting and non-inverting, because the V plus side is the non-inverting, so we can see that there's a difference in a voltage here, and so the voltage difference there goes up, the output voltage goes up. In this case here, when I connect it around the other way, as the voltage difference goes up, the output voltage here goes down. Okay, so it inverts it. So that's how you get the term inverting and non-inverting. Okay, so just as a reminder, the V plus side is the non-inverting side, and the V minus side is the inverting side. Okay, so let's have a wee look inside the Opamp. Now, it's not a course on RF analog design, although I have designed a few of these in the past in ICs. I worked for 7 years as an analog RF IC designer, mainly doing bipolar stuff, which is what we have here. But what we're going to have is a typical Opamp here is going to have 3 stages. So you're going to have an input stage, you're going to have a gain stage, and you're going to have an output stage. So the input stage here is a differential amplifier, so it amplifies the difference between these 2 voltages, V1 and V2. So don't worry if you've not seen this before, we're not going to be using this and we're not going to be designing it at this level. It's just to give you an indication of what an Opamp is. So that input stage passes on to a gain stage, which again is another differential amplifier, and it amplifies, this gives us most of the gain in the amplifier, and then it passes on to an output stage there, which allows us to drive lots of different loads. Now, also at the bottom here, this is just set up, this is just the biasing stuff for the circuit. Okay, now an actual 741 is a little bit more complicated, but ostensibly it's just the same as what we have above. We've got a differential amplifier input stage, we've got another amplifier gain stage here, and we've got an output stage here as well. Okay, so you might be sitting here thinking, well, what's the point in this device? If all it does is take a small voltage and amplifies it, and all it gives out is either the positive rail or the negative rail, what is the point in it? Well, I never mentioned it before, but we can use it like that as a comparator, and we'll get to that in another video, but that's not really the main use for this circuit. The main point here is that something called negative feedback. Okay, so this is really the main point of using an amplifier with a huge gain, because if you were to use negative feedback, it gives us very, very nice and very useful qualities. Okay, so let's go ahead and we'll consider using negative feedback. So the way the negative feedback works is we take the output and we feed some of it back in, or all of it back into the V minus, which is the inverting input. So let's have a wee look at this here, and we'll describe it in a kind of hand waving way, and then we'll go and we'll have a wee look at the actual derivation. Okay, so in a hand waving way here, if we take the output there and we feed it back into the input, so that's our negative feedback, it's fed back into the inverting input, the V minus, then we can see that if the input voltage there was to go up, then it would mean that the difference between V plus and V minus would go up, and we would take that difference and we would multiply it by a huge gain A, so it means that the output voltage there would go up. But if the output voltage was to go up, the output's connected back to the V minus, so it means that the V minus would go up in such a way that with negative feedback it tends to make the V minus equal the V plus. So it tends to keep these two voltages the same. So that's the main point of using, one of the main points of using negative feedback. But that's just a kind of hand waving explanation. So here's an actual derivation. Now, it's not the kind of thing I keep in my head, but once you've seen it once, you see it's quite neat, and you always know where to go and get it if ever you have to look it up. Okay, so if we were to look at the Opamp, the Opamp's output is, and I'll just read through this. Okay, it's going to be V out is equal to the gain A times V plus minus V minus. But we know from the circuit above here that our V out is equal to the V minus because we've connected them together. So it means that we can replace this V out here with our V minus. And then if we multiply out the right hand side, we're going to get this here. And then we can take across to the other side, we can take this term here, the minus AV minus across to the other side becomes plus AV minus, and then we can take out a factor of the gain A from each of these, so you'll be left with V minus upon A plus V minus equals the AV plus. Cancel out the A's on either side, and you're left with V minus upon A plus V minus equals V plus. So you can see here then that the main point is that the gain of this amplifier is so huge that if we say that the gain tends towards infinity, then we can say that this term here is going to tend towards 0. If this term tends towards 0, then the whole thing is going to tend towards V plus equal V minus. Okay, so that's a little derivation of what we have above. Okay, so in the circuit above there, we've got our V minus equals V plus equals V out. So this is an amplifier actually of gain of 1, and it's actually a useful device. It's called a unity gain buffer, and we'll have a look at it in one of the videos that is to follow, and we're using that for impedance matching. But now the main point to pick out from this point here is that an amplifier with a huge gain and negative feedback is a very useful device, and we're going to see that over the rest of the course, and we can see how we can use it. Now finally, I'm not going to get into any major detail here because it's a bit more detail than we need at the moment, but it's just to give you an indication of the ideal and the practical characteristics of an Opamp. So the left hand column here gives the ideal characteristics, and the right hand gives the practical characteristics of an op-amp. So ideally the gain would be infinite, but the gain, as we've seen, is around about 100,000 potentially, which is 10 to the 5. The input current, now we don't want any current flowing into the inputs, that's the V plus and the V minus, so ideally we want the input current to be 0, but typically we're maybe going to get 80 nanoamps. Now the frequency dependence of this, ideally we want it to, the bandwidth to equal infinity, meaning we want it to amplify signals by the same amount irrespective of what the frequency is. So it'll amplify a 1 meg signal or a 100 meg signal the same way it would amplify a 10 Hz signal or a 100 Hz signal. Okay, ideally we want that bandwidth to be infinite, but a typical op-amp there, we're going to have a 0 dB gain. Now I'm going to go over dBs in the next video, so don't be worried if you've not seen that before, but a 0 dB gain up at open loop gain up at 1 megahertz. Now again, don't be worried, we'll go over these in the next few videos, okay, so don't worry if you've not heard that before. The output voltage, infinity, but obviously it's going to be stuck by the power supply rails. Output impedance is 0, but really it's going to be around 75 ohms. The power consumption 0, but you're going to have some power consumption, roughly maybe 50 milliwatts. And the last three here, I don't really want to get into major detail, I just left them there just to kind of finish it off. There's some called the common mode rejection ratio, which we'll go over in another video, and should be infinite, but we're really going to get around about 90 dBs. The power supply rejection ratio is 0, but we're actually around about 30 microvolts per volt, and an input offset voltage is 0, but we're going to get about 2 millivolts. So don't worry, we'll talk about that in other videos. Now, what's the main thing to pick up from this video really in conclusion, and we can use to go forward onto the next videos, that just the bare guts. So the bare guts of it is that if we have an amplifier with negative feedback, then it will tend to make the V plus equal V minus, and also we don't have any current flowing into the inputs. Okay, so we're going to use these two little facts here, which we'll look at in a different video called the golden rules, along with some circuit analysis that will allow us to then go and look at some op-amp circuits. But before we get into any of that detail, I'm going to go over decibels. So I'll go in it in kind of some detail, and we can give you a good indication of how to use the decibel. So thank you for listening to this video, and I'll get you on the next video. Goodbye.